Good morning, good afternoon, good evening, whichever it is for you right now. This chemistry video tutorial is going to be on significant figures, and this should follow the dimensional analysis video. So if you have not watched the dimensional analysis video, please go back and watch that one first and do the practice. For this one, though, we will start with a dimensional analysis problem, just as a warm-up. I have convert 5 kilograms per liter to milligrams per milliliter. Go ahead and pause this video and work out that problem, and then hit play whenever you're done to check your work. Alrighty, so here's the way I worked out the problem. It's the same way I showed you before. We're starting with what we're given here. We're given a density. You can tell because it's a mass divided by a volume. We have 5 kilograms per liter, or just 1 liter. And I chose to start with the mass, or to convert the kilograms first. You could have started with the liters, and that would have been fine too. I started by converting the kilograms into grams, and I just placed the units first. And then since I didn't want grams, I wanted milligrams, I had to cancel out the grams and then convert to milligrams. Yes, you can skip steps and go from kilograms straight to milligrams, but I personally don't know that conversion. I'm not going to remember to put 1 million over 1, but what I do remember is the amount of grams in a kilogram and the amount of milligrams in a gram, going back to that base unit. All right. After I did that, I went ahead and changed the liters. Since liters is on the bottom here with what we're given, we have to move that unit to the top to cancel it out and convert that into milliliters. After I plugged in my units, I went in and plugged in numbers. So we know that 1 kilogram has 1,000 grams in it, and that's our conversion factor. And similarly, 1 gram has 1,000 milligrams in it. On this side, we have 1 liter has 1,000 milliliters in it. How you remember that is those units, those metric unit prefixes that I gave you in the last video. Once you're done, you can just multiply across the top and bottom and divide. I skipped that step. I shouldn't have, but I should have showed you. But all of my units canceled. And then you'll notice this 1,000 on top cancels with the 1,000 on the bottom. So I just saw that 5 times 1,000 will equal 1,000, or 5,000, excuse me. And my units that I'm left with is milligrams per milliliter, which is exactly what I wanted. Okay, so just a quick review there, but moving forward, what do we want to accomplish in this video? You should be able to use conversion factors to complete multiple step dimensional analysis problems. That's what we just covered here. Really, these two are the ones we're going to focus in, and definitely this one in the center. So students can report their answers to calculations with the correct number of significant figures. That's what SIGFIGS is, significant figures. And also, you should take note of how do these numbers reflect the way that scientists collected their data. The reason we use significant figures is going to relate to the way that data is collected. Alrighty, so get your notes ready. This is new. Rules for significant figures. First of all, what does that even mean? Significant just meaning that it's an important number is kind of what significant means. And the figure is the number. So when we say figures, we're talking about these numbers here. Which one of these are significant? Okay? So when we're counting significant figures, you always want to count digits 1 through 9. So if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, those are all going to be significant. Zeros is where we're going to have some sticky rules going on. You're always going to want to count sandwich zeros is what I call them. But what that is a zero that's between a digit 1 and 9, or 2 digits between 1 and 9. 2005 is a good example because you have a 2 here, a 5 here. These are both significant because it's between 1 and 9, and these zeros are sandwiched in between them. This is 4 significant figures. You will never count leading zeros before a digit 1 through 9. So in this example, we have 0.0006 All these zeros come before we even get a 1 through 9 digit. These are all leading. We don't count them. That's one significant figure in this number. Now this rule is the weirdest one. Sometimes we count trailing zeros following digits 1 through 9. Trailing being the opposite of leading, coming after this digit. So we will count trailing zeros if there is a decimal point present. So in this case, we have 600.0. Because this decimal is here, all of these trailing zeros are going to count as significant. This is 4 significant figures. We will not count trailing zeros if there is no decimal point present. So if it's just 600 written like this, because there's no decimal point, these trailing zeros do not count. That's one significant figure. So let's try these ones. You can go ahead and pause again and then unpause when you're ready. It's kind of awkward. Normally I would give you time to try it in the classroom and ask questions. But let's look at this number here, 8.450. First, I'm going to check for any digits 1 through 9. I see 1, 2, 3. So that's 3 significant figures so far. Then we have a trailing zero here. So we have to ask ourselves, is there a decimal present? Yes, there is. So this trailing zero does count. This number has 4 significant figures. Okay, let's try this next one. We have 300. Do I have digits 1 through 9? Yes, there's 1. It's 3. But there's 1, 3. And then I have 2 trailing zeros. These trailing zeros are not followed by a decimal. There's no decimal in this number, so they are not significant. This number has 1 significant figure. 10 decimal point, that is a way you can write the number 10. What this tells us is, let's see, we have 1 digit, 1 through 9, so that's 1. We have a trailing zero with a decimal, so this trailing zero does count. That's 2 significant figures. And last but not least, we have 500,000. 500,000, let's see, there's 1 digit, 1 through 9, and there's 5 trailing zeros. But there's no decimal, so they don't count. Only our 5 is significant. I hope you got all those right. If that's confusing in any way, please, please, please shoot me a chat and let me know. So what is the point? That's kind of the big question on students' mind. Like, why do we care what numbers are significant? What is the point? Well, significant figures communicate to us and other scientists the degree of precision used to measure a value. It measures the degree of precision used to measure a value. Precision is just saying, how exact were your measurements? I have an example, it's coming. Oh, look at that. Precision is the exactness of a measurement or a number value. So I have 2 scales here that we could compare. Let's say we put the same sample on either scale and measured them. And this scale tells me 3.00 grams is my sample. And this analytical scale or balance over here is going to tell me 3.0211 grams. It's the same sample, but one is giving me a way more precise answer than the other one. And you'll notice one is a lot more expensive than the other one. It makes a lot more sense when you're actually in a lab because just the quality of the balance that you're using is going to give you a more exact measurement. What this one is going to do is going to introduce some error and some measurement error where because our tool wasn't perfect and it wasn't precise enough, we really can't say that this number is truly 3.00 grams. That's why it matters. That's what it comes down to. You're probably thinking to yourself, well, I'm not in a lab right now. I'm sitting on my couch and I'm watching this video, right? Well, when you do go into a lab, or if you choose to pursue science further than high school, this is something that is just expected that you just know intuitively how to do. So it's a good habit to get into in your high school science classes. Okay? So when we do calculations in a science class, we want to make sure the answer we circle has the correct number of sig figs. Yes, it will count. So when we're multiplying and dividing numbers, which is mostly what we are going to be doing, the number with the least amount of significant figures limits the precision of all calculations. The answer should reflect that by having the same number of significant figures as the least precise measurement. Okay? So let's say we were going to multiply these numbers, and we want to make our answer have the correct number of significant figures. So I'm going to pull my calculator out on my phone. I have 4.05 times 5.006 times 3.000. It gives me a large number. It says 60.8229. That number is 1, 2, 3, 4, 5, 6 significant figures, and that's not correct. It's mathematically correct. Scientifically, it just shows me you forgot to tell me how precise were your measurements. So let's go ahead and count the significant figures for each of these. This number, I see 1, 2 digits, 1 through 9, and a sandwich 0, which we always count, so that's 3 significant figures. This number has a 5 and a 6, and 2 sandwich zeros, so that's 4 significant figures. And then this one has a 3 with 3 trailing zeros. So that's 4 significant figures because there's a decimal point. So we have 4, 4, and 3. This number right here, 4.05, has the least amount of significant figures, which means it's the least precise. So we're going to want to round our answer to have 3 significant figures. In this case, it would be 60.8. All right, I'd even put the answer in there. Go me. When adding or subtracting, instead of counting the number of significant figures like we do with multiplying and dividing, we'll round to the least precise place value, which is a bit different. So in this case, I have 401 plus 16.8. 401 plus 16.8. That's 417.8. I could have totally done that in my head, and I chose not to. In this case, because my answer is 417.8, I'm not sure where I should round. We have to look at the least precise place value, which is going to be the one furthest to the left. So in this case, we have what is this one called? A tenths place? Yes. We have the tenths place here is the most precise place value. And on this one, we have the ones place is the most precise place value. The ones place is less precise than the tenths place, so we're going to have to round to this ones place. Our answer would round up to 418. We won't run into this as much as this, but it's worth it to note. In both cases, we can round or use scientific notation to report the correct number of significant figures. If you're not sure about scientific notation, please let me know and we can talk. I don't think I'm going to do a whole video on it unless it's clear that everyone needs some help on scientific notation and rounding. I will make a poll. I have some practice problems here that are optional for you. Significant figures is one of those things where a lot of people tend to grasp it, so I don't want to spend too much time here or force you to do practice. But if you're thinking to yourself, oh, I'm not too sure about this, I think I need some more practice, please, please, please check out these problems. This is an old PowerPoint, so back in the day, I would have you do these in pairs. And times have changed. It's kind of sad. There's also some more practice here in your textbook. There's also dimensional analysis practice here. I'm actually going to be hosting an optional office hours where if you guys want to do this practice live with me, I will make that happen. And it can be a little bit more interactive so you can ask questions in real time. I will do that on Friday from 1 to 2. And it's optional, so don't feel like you have to come, okay? And there's just some more problems here. It's not homework. It was homework one time. This is not homework, but it's just some more practice problems there. Okay, that is everything. Again, let me know if you have any questions, and I will be here.